This comes out of section 4.4, Applied Max-Min Problem. Used to make a box with a square base and an open top. Find the largest possible volume of this box. You want to draw a box of this type that has a square base, so these dimensions are the same, and then it has an open top, so you don't need to be an artist. In fact, I have my moments where I'm definitely not an artist. Let's define some variables. I might call this base x, so it's x by x, and then call the height of this thing y. So it's not a cube, but the base of it is a square. And its top is open, but that's kind of hard to draw. So the largest possible volume means the objective here is to maximize volume. So volume equals length times width times height for a box. So in this case, volume equals x times y, so x squared y. I don't want to just take the derivative of that because I've got an extra variable in there. But the constraint is just that they've told me how much material I have, which is basically the area. They've given me 4,000 centimeters squared of material is to be used. So, the units are a clue that that's an area. But so the area of this box is going to be the base. So 4,000 centimeters is equal to x squared plus the area of the four sides, which are each xy, so 4xy. So there's my constraint. There's no top, that's why there's not another x squared on there. What I do with that is I solve for one of the variables. Now in this case, solving for y is going to be the choice that makes sense. Y equals 4,000 minus x squared divided by 4x. I take that expression for y and I substitute it into my objective equation, which gives me volume equals x squared times 4,000 minus x squared over 4x. Now I've seen people dive in now with both feet and start taking the derivative and use the quotient rule and the product rule, and it's great, you can do that, but you can save yourself a little bit of trouble by simplifying your expression before you start multiplying or before you start differentiating. I've got 4,000 x squared minus x to the 4. Everything is divided by 4x. So this can be written as, probably the best would be to say 1,000 x minus x cubed over 4. Definitely an easier derivative to take. It doesn't require any product rule or chain rule, quotient rule, any of that, because I can say, well, the derivative of that, dv by dx, equals 1,000 minus a quarter times 3x squared, or 3x squared over 4, if you like. And I do the same thing with this derivative that I've done in other Max-Min problems, which is let that derivative equal 0. So if I solve this, I've got 1,000 equals 3x squared over 4. So multiplied by 4 divided by 3, I've got 4,000 divided by 3 equals x squared. So x equals the square root of that, and plus or minus, but you're not going to have negative dimensions of a box, so the square root of 4,000 over 3. If I was asking you for exact values of the length of the base or something like that, you'd be basically done. You could rationalize it and make it look a little prettier, but that's it. That's how big this base of the box is. But we're asked for the largest possible volume, so we actually want to say, what does this volume equal? And so I need to say, well, volume equals 1,000 x minus x cubed over 4. So let's put in some numbers and figure out how big a box we actually have. You crunch those numbers and you find that this volume is approximately 24,343 centimeters cubed. If you're asked the dimensions of the box, you'd need to find x and y. X, when you do figure out what the square root of 4,000 over 3 is, it's just about 36.5, a little bit more, and you'd have to find y. But in this case, we're answering the question by saying the largest possible volume of the box is just over 24,000 cubic centimeters.